probability that an event occurs is between 0 and 1. And if your probability is 1, that means it's guaranteed to happen. Ben Franklin said that there's 2 things in life that are guaranteed: death and taxes. Both of those will occur with probability 1, at least according to Ben Franklin. On the other end, we have things with a probability of 0. And a probability of 0 means it's impossible. And until this season, the Lions winning the Super Bowl, I used to lump down at this end of the spectrum. For everything in between, you have various degrees of uncertainty. You've got a coin flip, which is more or less a 50-50 proposition. You got things that are likely, things that are unlikely. So it just kind of depends. Now, how do you get these probabilities? Well, that's going to depend on, what you're working with. A lot of times we do things with what's called the classical approach. That would be just like the stuff that I just did, which would be flipping a coin. There's 2 possibilities and there's only one that represents success. For those of you who are fans of role-playing games, here's a few role-playing dice. The tetrahedron, the octahedron, and the dodecahedron. 4, 8, and 12-sided respectively. So for instance, the probability of rolling an 8 is 1 out of 12. So that's the classical approach. You define how many ways something can occur and divide it by the number of what are called simple events. So we'll work with both of those. Now, it's fun when you can do this, when you do things this way, but you can't always do things this way. So there's other ways you can get at probabilities. So one way is with a relative frequency approach. For instance, if you want to find the probability of getting struck by lightning, well, you can't exactly define a sample space and then count the number of simple events. But what you can do is you can look out in a particular region and find the number of occurrences of an event. Let's see, so like you could find how many lightning strikes there were divided by how many people there are in a certain region. And it turns out that Florida is where you have the best chance of getting struck by lightning. So I'm not sure where Michigan is and all that. So that's a couple of different ways you could work on probabilities. The last one that we're going to consider in this book is a subjective probability, where you just ask somebody who's an expert, what do you think the chances of this happening are? And they kind of hem and haw, and they just say, shrug, and say, well, 30%, 50%, whatever they think. But it's not something that you can actually really write down. So those are a couple different approaches. We're going to mostly concern ourselves with these 2 approaches. But let's just double check our understanding on one key thing first. And that is jumping down to example B. Let's see if we can't figure out which one of these things are legitimate probabilities. So try and circle or otherwise indicate which one of these are valid probabilities. Now let me kind of head something off at the pass here. I'm not really a big fan of 50-50. I know what they kind of mean here. I mean, one way to look at this is 50 minus 50 is 0, and that's a legitimate probability. But, I don't know. I don't really like that one. If you want to say a 50-50 chance of something happening, then in my mind, that probability would be 0.5 or 0.50, whichever you want to use. But go through the rest of them and see what you think. Try and decide which one of these are actually legitimate probabilities. All right. Another few seconds. Lily, let's start us off with the first few. These many. Which ones should I circle? Which ones should I cross out?
You can circle 0.
Good.
Cross out the negative.
Good.
And the fraction, you can circle 3 out of 5,
Mm-hmm.
cross out backwards.
Nice, nice. Well, let's keep going. Matilda, let me ask you. Let's look at the next few. Which one of these should I include as legitimate probabilities? Which one should I cross out?
Keep 1.
All right, we'll keep 1.
Cross out 7 to 3.
7 to 3 is an odds, so odds aren't probabilities. We can turn them into probabilities. And how about 5 to 1? Well, that's also an odd. And Maddie, the last two.
I circled both of them.
Circle both of them. Dylan, do you think she's right? Should we circle both of these?
Me?
Yeah.
I crossed out 2.017.
Yeah, 2.017 is more than 1, so we don't want to include that as a possible probability. It's just too big. You're not going to have something with more than 100% chance of happening. So certainty stops at 1, and we don't go any higher.
Are we keeping 50-50? Just random?
You know, if 50-50 is here is supposed to mean 0.5, then I would keep it. I don't like the way it's written here. I just wouldn't put that on an exam for myself. It just bothers me. So if you regard it as 0, then yeah, we would keep 0. If you regard it as 0.5, you keep 0.5. I just don't like that one. So that one I would get rid of, really. All right, let's keep going. Who discovered penicillin? Marcel Beach, William Penn, Johannes Salk, Alexander Fleming, or Louis Pasteur. So what's the probability that you correctly guess of these 5 gentlemen that Alexander Fleming discovered penicillin?
5.
Yeah. So probability of a correct guess, there's 1 correct guess out of a total of 5 possibilities. So yeah, thank you. 1 out of 5. All right. Now we're not always going to be quite so lucky to have such a simple problem. Let's take a look at example D, for instance. In a Pew Research Center survey, and by the way, if you see Pew Research Center, they're a pretty respected statistical organization, so you can give their results, the appropriate weight. They randomly selected adults that were asked if they have seen or have been in the presence of a ghost. 366 of the respondents answered yes, and 1,637 answered no. Based on the results, find the probability that a randomly selected adult says that they have seen or been in the presence of a ghost. So, okay. So this is example D. At least the first part. So I want to find the probability of seen or been near a ghost. So probabilities are often expressed as fractions. You could also do those as decimals. But, okay. It's going to be a little more involved than the 1 out of 5 that we had for the first one. So in the numerator, we got to put the number of ways you could succeed. How many ways are there we can succeed in this experiment?
366.
366. Good. And in the denominator, we got to figure out, well, how many possibilities are there overall?
2003.
Ah, well done. A couple of you got that. And it's more than just divide by 1,637, because that's the number of no respondents, 1,637. But you've got to also include the rest of the people that were contacted in the survey, the 366 here. And that overall gives you a total of 366 over 2003, right? All right. Beautiful. So you have to be careful about, if you need to add things to get the denominator, correct denominator or not. Are we okay with that first part of example D? Yeah, doing good there? All right. Let's take a look at the second part. So, in a particular survey of internet users, 3,782 respondents say that they use social networking sites, and 1,373 respondents said that they do not. What's the probability that a randomly selected person uses a social networking site? Does that result suggest that it is likely, with probability greater than 0.5, for someone to use social networking sites? So, So probability that they use social networks. So again, you got to put together a couple numbers. So let's highlight some of the things that we need here, and here. All right. Hermione, what do you suppose I'm going to put in the numerator?
3,782.
Good, 3,782. And Jordan, what should I put in the denominator, please? Perfect. So we need to add those two things to get our denominator. So overall, that's going to be 3,782 divided by 5,155. Generally speaking, I'm happiest when you give me fractions because people make mistakes calculating things and rounding things. So generally it's happiest when I see fractions there. You can, if you want, give me your percentage there. So 3,782 divided by 5,155. And where I care about it, I'll tell you how many digits I want things rounded to. In this case, quite often I'll go with the fourth decimal digit, so about 0.7337. If you're rounding to the nearest 10,000th there. So you got a 5 to the right of that 6, so that means you round up the 6 to a 7. There you go. But where I want a decimal and how many decimals, I'll specify if it really matters to me. All right, not so bad, not so bad. Let's look at something called the sample space. So, sample space. The sample space is the collection of all simple events or outcomes from an experiment. So, sample space is the collection of all outcomes or simple events of an experiment. So all the things that can happen basically is what a sample space refers to. So in example E, they asked us for the sample space for 3 births. So for 3 children, what are the things that can happen? Well, let's see. Let's start out with girl, girl, girl. Or you could have girl, girl, boy. And then girl, boy, girl. And girl, boy, boy. So that's 4 things that can happen. But because each of these events, each birth has 2 possibilities, I expect really 2 cubed or 8 possibilities in my sample space. So let me go through and find some more. The other possibilities, you could start out with a boy and then have 2 girls. Start with a boy and then a girl and then a boy. And then boy, boy, girl. And finally, boy, boy, boy. So that's the collection of all 8 things that can happen. This collection is your sample space. So it's a sample space for the genders of 3 kids. All right. So 8 things. Now, some of these are, in a sense, equivalent. I mean, there's a few events where you have 2 girls. So you have 2 girls here, 2 girls here, and I think there's one more with 2 girls, 2 girls here. So those are equivalent, but those become compound events where you're adding up all these simple events. These are as basic to this events as the events can get for this experiment. So that's your sample space. All right, nice. So what's the probability of all girls?
1 of 8.
Yeah, all girls would be 1 out of 8. Probability of 2 girls would be 3 out of 8. All right. We're going to extend our work with probability with some definitions on the next page. So example F. I'm going to talk about things that are the complement. So A bar is the complement of an event. So basically A bar is everything but what happens in A. So it equals the event of having, let's see. Now actually let's do this first example here. We'll talk about event A and event A bar a little bit more. I'm going to apply A bar to a particular example. So let's say the event of rolling a 4 on a 4-sided die is my event A. The event A bar would be rolling a 1, 2, or 3. It's rolling anything else. So you've got A bar and A. Those are the only things that can happen. Either, for instance, you roll a 4. It's really pretty warm. I guess that it's a 4. You roll a 4 or you don't roll a 4. Those are your only alternatives. So let's apply that to this down here. And it's nice to keep in mind something like this. The probability of A bar or not A bar, when we add those up, we get 1. So what that's saying is that the probability of getting a heads or not getting a heads, and when you add those two together, you're going to get 1. One of those 2 things is going to happen. Once you have this in mind, you can rearrange things. You can get things indirectly. The probability of A bar is 1 minus the probability of A. And likewise, the probability of A is 1 minus the probability of A bar. So it's the complementation rule, and it's really, really helpful. We're going to use it a lot. So in this example, it says A is the event of of 4 randomly selected bursts resulting in 4 girls. The probability of A is 1 out of 16. What I want you to do is, first of all, with this as your definition for event A, try and describe what A bar is. What does A bar mean in words? Not worrying about the probability just yet. You get to that in a second. But what does it mean to be the event A bar? All right, confer with a neighbor. What does it mean to have the event A bar.
Yeah, it's like what random. That's like what.
Yeah, what I was thinking was like A bar is just like all the
This
other
bar
like
is
possibilities that didn't happen.
It's like how you make it.
Like because A bars four rounds.
A is the original.
Okay.
I'm guessing everything. You will never think we should just.
Well, if it adds up to one, then it have to be like all the other like chances to make it 100.
All right. Does someone have a good definition of what the event A bar would mean? What's happening there in A bar? Elijah? I'm sorry, Dallas. What does it mean to have A bar, the event A bar?
Would it be boys?
We'll tell you what. Let's take a look at it this way. This number line represents the number of girls in our experiment. Event A, what would I have to circle for event A? What goes along with event A? How many girls do I have?
4.
4. So this is event A, right here. That's my event A. So everything else is A bar. Event A is, everything else. So this would be A bar. So you got A or A bar. For convenience here, maybe I can write number of boys would be 4, 3, 2, 1, or 0. So there's a couple ways you could write the event A bar. It's one of them. Event A bar means what? A bar. Well, one way is to look at what this is. How many girls do you have in event A bar? Either 0, 1, 2, or 3. All right, so event A bar is the event of, at most, 3 girls. Okay. There's another way to describe it. In terms of the number of boys. Event A means you have 0 boys. What's the event A bar in terms of boys? How many boys do you have to have if you're in A bar? What's a way to describe that?
At least one.
Yeah, at least 1 boy. Thanks, Dylan. So there's a couple ways you could think of it. But these ideas of at least and at most, those are going to come back at us. So hopefully you're starting to get a little bit familiar with it. Pardon me, we'll certainly have time to practice it. But let's actually calculate the probability. The idea with the probability here is that I don't want to have to calculate all these different probabilities. I just want to do one calculation. Probability of A bar is going to be 1 minus the probability of A. But they gave us a probability of A, right? What was the probability of A?
4 girls? Or 1/16?
Cool, 1/16. Now, if you're not good with the subtraction of fractions and stuff like that, and you know your instructor is kind of partial to that, let me direct your attention to your graphing calculator. You can do 1 minus 1 divided by 16. Now that's going to give you a decimal. And you might remember like, oh yeah, he doesn't really like decimals. If you hit the math key and press enter twice, that'll turn that into a nice, neat fraction. Now keep in mind, not everything can be turned into a fraction. For instance, very famously, square root of 2 is not able to be written as a fraction. So if you try, press enter twice there, wrong spot. Second, I don't know, over here, math, enter twice. It just comes back with the same thing. But a lot of the stuff that you're going to work with can be written as a fraction. So if it can be, I generally like it as a fraction. Overall, we get 15 over 16 here. Let's try another one, kind of like the one up above. A certain group of women have a 0.43% rate of red-green color blindness. If a woman is randomly selected from this group, what's the probability that she does not have red-green color blindness? First of all, is a 0.43% chance, is that a big chance?
Pretty decent.
Gotta be a little bit careful here. So, probability of, I'm just going to say color blindness is 0.43%. But what's tricky is that you got to remember that the 0.43 is already a percentage. So if you turn that to a decimal, it's 0.0043. So now let's look at that. Is that a big chance of color blindness? No, it's not. But we want to know what's the probability that she does not have red-green color blindness. So what is that? Does not have. How could I write that? Be the probability of, is it the probability of C bar? Yeah, it's probability of not having that. How could I calculate that? Any suggestions?
100 minus 42, get the difference.
All right, so we get the difference. So it'd be 1 minus 0.0043, which gives you 0.9957. Is it likely that if you pulled somebody out of this group that they wouldn't be colorblind in terms of red colorblind? Yeah, that's a really good chance. There's only a 43 out of 10,000 chance that you would find somebody with red-green color blindness. So, nice, nice. But see, what we're doing is we're calculating probabilities indirectly. And that's quite often what we have to work out, is with things indirectly. Let me mention something quickly about the rare event rule. Something's a rare event if it happens less than 5% of the time. So, rare events happen less than 5% of the time. So that's a little remark there on the rare event rule. I think, this is just a guess on my part, that this standard kind of goes back to a remark by a mathematician, statistician named R.A. Fisher, who was very influential around the turn of the 20th century in statistics. But let's apply it to example G here. Y-sort gender selection technique is designed to increase the likelihood that baby will be a boy. They've also got an X-sort as well. At one point, before clinical trials of the Y-sort gender selection technique were discontinued, 291 births consisted of 239 baby boys and 52 baby girls. So, I'll just do it this way. 291, 239, 52. Based on these results, what's the probability of a boy born to a couple using Microsort's Y-sort method? Does it appear that the technique is effective in increasing the likelihood that a baby will be a boy? So let's first of all calculate the probability of a boy amongst these results. Probability of a boy. What's that probability in and amongst these results? What, over what?
239.
239 over which? 291. Do we agree with that?
Yeah.
Yeah. We did notice we didn't have to add things together. I mean, even though they gave us both numbers, they already gave us the sum for the denominator. If you take out your calculator, that's about 82.1%. So, what do you think? Was it effective? Oh, yeah. Later on in this course, when we do binomial probabilities, we'll be able to calculate the probability of an event like this or something more extreme. But then an outcome like this would be extremely unlikely if this Y-sort method had no effect. That is, if there was a 50-50 chance, then it'd be really incredibly long odds to get something like this. Okay. So let's go down to the birthday example. Yay, we did the birthday example last week. My other class, my morning class, has more people than you guys did, and I still smile thinking about the results there. The last two people had a December 7th birthday. It was cool, worked out nice. But on their first date, Kelly asked Mike to guess the date, not the year, of her birth. What's the chance that he guesses correct? And we're not going to include leap years. Yeah, 1 out of 365. Would it be unlikely for him to guess correctly in the first try?
Yes.
Yes, it'd be very unlikely. If you were Kelly and Mike did guess correct on the first try, would you believe his claim that he made a lucky guess, or would you think he's cyber stalking you?
Cyberstalking.
All right, I might have ad-libbed a little bit there. So, yeah, I don't think I'd necessarily believe him. Let's see. So, would you believe his? No. No. And last one. And this shows a little bit of the sense of humor on the author's part. If Kelly asked Mike to guess her age, and Mike's guess is too high by 15 years, what's the probability that Mike and Kelly will have a second date?
0.
0. Yeah, it's just not happening. All right. Cool. Let's get into a discussion about odds. Okay. The odds in favor of a certain horse finishing second place are given as 20 to 80. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusive. And then we'll work on the payoff odds in just a minute. But let's take a look at example 5, 6, example I. So the odds that are given here are 20 to 80. And more often, that's expressed not with the word 2, but with a colon here. So it's 20 colon 80. And let's keep track of what each of these things means. 20, that's the ways to win. To win. So there's 20 ways to win, and this is the ways to lose. 80 ways to lose. I doubt you would see odds expressed like this very often. More often than not, they're going to put these in what are called lowest terms. So, for instance, if I treated this almost like an equation, what number could I divide both of these by evenly? 20. So if I divide this by 20, I get 1. This by 20, I get 4. Now that still represents the same thing. It still represents the number of ways to win compared to the number of ways to lose. But keeping this in mind, keeping track of what's what, makes it a little bit easier to figure out what's the probability involved. So if you want to know the probability of winning, what's that going to be? How many ways are there that you can win, according to this last ratio? One. But is it 1 out of 4 or 1 out of something else? How many possibilities are represented here altogether? 5. Well, there's 1 way to win, 4 ways to lose. So, all right. All right. So, yeah, 1 out of 5. Yeah, that's your ways of winning. Now let's discuss the payoff odds. So the payoff odds, that's defined for you down here. Payoff odds, the odds against that something occurs, the ratio of the net profit, how much you win, and the amount you bet. So the payoff odds look like this. The net profit colon how much you bet. All right. So it says if the payoff odds is the actual odds against winning. Now let's be careful about something. These are your odds for winning. They were 20 to 30. 20 ways you win, 80 ways you lose. Also 1 to 4. Okay. So let's look at the what the odds against winning would be. If the odds are for winning, what would be the odds against winning? Well, we just got to kind of turn things around. So let's just circle this for the moment. Here's your payoff odds. If these are the odds for winning, 1 time you win, 4 times you lose. These are odds against. I should have put against here, didn't I? Against. Maybe that's why you guys are quiet. Like, wait a minute. These are the odds against winning. No, those are the odds for winning. I was right.
Yeah.
I thought I was wrong, but I was merely mistaken. These are the odds for winning. What are the odds against winning? 4 times you lose. How many times you win? 1 time you win. So this is the number of ways to lose. Ways to lose versus the number of ways to win. Now, we're going to make those our payoff odds. So our payoff odds are 4 ways, are this, 4 to 1. This is the amount you bet. That's the amount you profit. But we're not making a $1 bet. We're making a $10 bet. So let's see if we can't modify this a little bit. What would I have to multiply both sides by to make this 10? 10. And if I do that, I get 40 to 10. This is how much you bet. How much is your profit?
The 40?
40. That's your net profit. So they'll actually hand you back $50, but only 40 of it will be your profit. because 10 was your original bet. So they have to give your original bet back. The rest is your profit. And that's it. That's all there is to that one. All right, so it's a little bit of working with odds. We're going to do another example of working with odds, just because it's something that's probably new to you. If you have a question at the moment, though, here's a good place to get an answer. Something that maybe I went over a little too fast, and you're like, well, I don't get this, or something else. Doing good on those? The first one? All right. Let's try the next one. And in as much as we got gambling in this town, we're not going to go with the fictitious example that they have in the book. Let's go with a real example. All right. Join. So in order to do that, we got to make a couple modifications to this problem. I'm not sure if you guys are familiar with a roulette wheel or not. But if you're not, then I think I got a picture right here. This is the one we want to look at. A roulette wheel has the numbers 1 through 36. They're either colored red or black. It additionally has two other numbers. You've got a 0 and a 00. Those don't count as black or red numbers, nor do they count as even or odd. So here's your 0, here's your 00. So let's, like I said, modify this problem a little bit. So we'll scratch out the word modified. A roulette wheel has 38 slots. One slot is 0, another one's 00, and the rest of the numbers 1 through 36 are numbered 1 through 36 respectively. You're placing a bet that the outcome is an even number. What's your probability of winning? Now, in roulette, 0 and 00 are neither even nor odd. So, all right, let's think about the probability of winning first. Well, so there's example J here. Example J, part A, probability of winning. Well, how many slots could that ball fall into when you spin the wheel and roll it? 38. Only half of those, half of this number, are going to be your even numbers. So what's half of 36? 18. Nice. So that's your probability of winning. A little bit less than 50%. Okay. What are the odds against winning? So, odds against. And for that one, you've got to kind of tear into your probability above just a little bit. Odds against are the number of ways against something, colon, the number of ways it can happen. So according to our probability above, what are the number of ways that you can get a 38 or can get an even number?
Or no, it's 18 still.
18. That's the number of ways it can happen. But you're right with thinking about the 20. If there's 18 ways it can happen, what's the rest of this number got to be? 20. So the ways against it would be 20. Or you could also write it as, in lowest terms, 10 to 9, but 18 to 20, that's pretty good. So what you had to do is you had to split this up and realize the number of ways it could happen, the number of ways it didn't happen or won't happen. Now, typically speaking, when you play roulette, the payoff odds in a casino are going to be 1 to 1. So payoff odds are 1 to 1. That's the amount bet. That's your net profit. Bet and net profit. If you bet $18, what's your profit? At least in the way the casinos typically pay you. 18. You earn dollar for dollar. So if you bet 18, in fact, do what you can kind of think of doing this, and that is, if you take your 1 to 1 and you multiply by 18, that would be $18 profit for every $18 bet. So the profit would be equal 18. All right, cool. Let's change things up though. How much profit should you make on an $18 bet if you could somehow convince a casino to change the payoff odds so that they are the same as the actual odds? So the actual odds against, that was up here. That was our calculation up here. Odds against, or this one right here. So that's going to be our new payoff odds. Payoff odds are 20 to 18. So if we bet 18, bet $18, how much should we win? Don't make Haley answer her. Give Haley a break on this one. How much should we win? Keep in mind, this is still representing the same things. That's your amount bet. That's your net profit. Yeah, thank you. Is that George's? Wow. Okay, a couple people. Thank you. Who else?
That's it.
All right, that's it. Thank you. All right, so you should bet 18 and win 20. So wow. They're kind of keeping a little extra for themselves, aren't they? So the difference between, what you should win and what you do win, or in other words, the house's advantage on you, is something called the vigorish. It's not a term that's really a part of this course. But the vig or the vigorish is basically the house's advantage over you. And in the game of roulette, I think the house's advantage on you is about about 5.5%. So that house advantage over time is going to catch up to you. If you keep playing that game, eventually you will lose with probability 1. Yes, sir.
I kind of got a little sidetracked from the beginning. Wait, how did you get the 20 and 18 and the 30? Was it just something you?
So the premise of the problem here was if you could somehow convince the casino to change its payoff odds so that they're the same as the actual odds against winning. So the actual odds against winning is something we calculated up above. That was part B. So I just stole the odds from part B. Those are now the payoff odds. And that means if you bet 18, you should win 20. So that in a sense gives you the house's advantage of 5.5%. 5.5% in roulette. Now, in other games, that advantage is different. So, for instance, if you play correctly in the game of craps, you can get the vig down to less than 0.5%. That's a lot better. That gives you a much better chance of winning in the long run. Now, staying around long enough, you will lose. But your odds of staying in the game are better when this vigorish is smaller. Whatever you do, if you're going to gamble, it makes sense to learn the games that you're playing. Because, for instance, and I'm not trying to convince you to gamble, but I see a lot of stupid bets when I see people play. Craps is the game that I play usually. I like Big Six and Big Eight as a great example. If you play Big Six and Big Eight, it has a 1-to-1 payoff. So if you bet $6, how much do you win? $6. For the same risk to your money, you can bet $6 and win $7 if you place your money just someplace else on the crap table. Wow, that's an extra 18%. And you can even do better than this if you really understand the game. I'm not going to try and explain it. If you are going to gamble, make sure you gamble with money you can lose, because eventually you will lose. But there are good bets and there are bad bets in a lot of these games. And understanding them really makes a big difference. I've come back a winner more than I've come back a loser when I go to Vegas and other things like that. For some reason, I just don't gamble downtown. It doesn't feel as exciting. Vegas sounds more fun. But
I'm up on Caesars right now.
you're up on Caesars.
Just craps.
Craps is where you're going to give yourself the best odds, because there are certain bets you can make in craps that give you true odds. But anyways, I digress. I don't mean to really try and explain the game of craps, other than to say that, there are some smart bets out there, but don't gamble with money you can't afford to lose. Okay, let's do one last example here. Example K. So these are results of a drug treatment, a drug scanning test. And what I would suggest that you do first when working with this is, write down a few totals here for ourselves. So let's do some marginal totals. Those of you familiar with accounting. So down here, we're going to have 61. Over here, we're going to have 46. For a total of 107. Now those numbers better match up when I do this way, 54 and 53. Yeah, all right, that gives me 107 people went through this drug screening program. And you've got this cross table of results. So a question that could be asked would be this: what's the probability of a correct result? So of the 107 people, we've got to figure out, well, how many got a correct result? So probability of a correct result. What numbers here represent a correct result?
42, 34.
Nice. 42 and 34. That is, the subject used drugs and they got a positive result, or they didn't use drugs and they got a negative result. So overall then, probability of a correct result would be 42 plus 34 over 107. Don't forget to divide by that 107, otherwise it's just wrong. So we end up with 76 over 107. Yay. And that's it. Are those results high enough to make you comfortable using this test? No. No, that means, let's see, 176. That's only it's got almost a 30% failure rate. That's a lot of people. And the next part says, what's probability of random selection if somebody has a false positive? We can do that one. But who suffers from the result and why? So false positives, which one would be a false positive here?
19 over 107.
Yeah, 19 over 107. So probability of a false positive would be 19 over 107. Says who suffers from this result and why? Well, I think both people do, right? Certainly if you don't get hired because you got a false positive, that's bad. And if you're a quality candidate, and you don't get hired, then the company suffers. So both of them suffer. Nice, nice. All right. Comments or thoughts on example K here? All right. Let's call it a wrap for section 4.1.